Hey, Sam, you're lucky we could see your face. All you can see is my face that's overwritten with our last description of Maxwell's equations, and we're looking at using phasor notation to split off the time dependence. So here are the 4 Maxwell equations. Notice that there are no charges, so there's no charge sources here, and there's no currents. What? How can this be? It's common in most textbooks to neglect the source terms. Somehow the fields got there, okay? So they got there. Now,
so it's just some wave that got into a free space from a very far away galaxy.
Yeah, so we don't know. It's just there. Now, to make it easy, we're going to split off the space and time dependence. So for example, the electric field, which depends on space and time, we're going to represent it as the space part, and S stands, as we know, sinusoidal times a sinusoidal time dependence, e to the j omega t. Now, normally in most books, they don't put the omegas here, but when we use this, we're going to see later on that, in fact, omega enters as a parameter for all space. So every frequency has a different spatial kind of solution because the wiggliness is at different rates, i.e. the angular frequency. We do the same for H. So let's run this through. I'm going to take, we don't need to do all of these, I'll take this one. So I'll start with curl of H. Now, we write H like this, and we see that there's a time factor here that's not affected by the curl operator, which is in terms of space. So if we substitute this representation of H in here, I'll do the left side, you do the right side. We're going to get e to the j omega t times the curl of the spatial part of H, which is H depending on x, y, z, omega, and the s. And that's equal to, you get to do the right side.
Okay, I have it.
You got it.
Well, obviously epsilon stays here. When you substitute in the whole E phasor with E j omega t to this term, del E del t, the spatial parts do not depend on time. So actually only the E j omega t is affected by the partial derivative. So I guess we can extract this e to the s out. Well, es out, x, y, z, omega, and then d dt of this, you just take out the j omega.
Right.
J omega e to the j omega t.
So now, how do we simplify this? I'll do my side. We can cancel out each of us. There. And that's the phasor form of the 4th Maxwell equation, Ampere's law. That's what it looks like.
Looks okay?
And that, yeah, and those S, HS, and ES, of course, just depend on space and frequency. So now let's look on the next board a different example. Well, let's continue with our use of phasor representations, and we'll begin here with this great application of the wave equation for the electric field. We've seen wave equations before, but this is the 3-dimensional case, and of course E has 3 components. So let's simplify it a little bit. Sam, you take the left side, I'll do the right side.
Sure. I mean, the Laplacian is just this, as given. So I just write this down. If we substitute the E vector in to this E, we would get this long form. So I'll just write that. E phasor of x, y, z, omega, e to the j omega t equals...
And I get to do the right side. So, same idea, let's continue on. 1 over v squared. Now, second derivative of the complete field described like this in phasor form. E, S, X, Y, Z, omega times e to the j omega t. So this whole thing is time differentiated. And now if we simplify it, we will get an equation only involving
The phasor E.
the phasor E, ES. Notice that things will happen to the exponentials to simplify, and you'll right away see now why we have the omega here for ES. And I think that's all we have to say about phasors.